Hello viewers, in this video we're going to derive the Arrhenius equation at two temperatures. So the Arrhenius equation at two temperatures is the most used formula or equation to calculate or find the value of activation energy. So it's driven from the standard Arrhenius equation that is given by K is equal to A, E given to the power of minus EA over RT. So that's what we have there. Now, this is the standard form of Arrhenius equation. It shows the relationship between the rate constant K, temperature, and activation energy. So yeah, where K is the rate constant, A is the frequency factor, R is the ideal gas constant, T is temperature, Kelvin temperature, and EA is activation energy. So let's see how we can drive the form which includes two temperatures. Now the first step is to bring down the activation energy in this case. So this expression that is given as a power to E, we want to bring it down. How do we bring it down? We need to introduce, remember E is an inverse of natural log. So we need to introduce natural log on the left hand side and also on the right hand side. So let's quickly do that. We are saying we're introducing natural log on the left hand side and also on the right hand side like that. So have natural log of A, E given to minus EA still over RT like that. Yes, so it's natural log of everything that we have there. After doing that, this will continue to say we have natural log of K being equal to, now if you have natural log of XY, this is the same as natural log of X added to natural log of Y. So this same concept here is what we are going to use even in this case. So we'll say what we have here is natural log of the frequency factor A that will be added to natural log of E that is given to the power of minus EA over RT like that. Just get rid of this part. Yes. So we continue there. So this will be, we'll have natural log of K being equal to natural log of A that is added to. Now we said this natural log and the E are inverse of each other. So whenever they meet, they cancel each other. So those two will go, and what we're going to have is our minus activation energy over RT is coming down like that. So this is what we are going to have. And continuing from here, we'll say we have natural log of K being equal to the natural log of A. Now, when you multiply negative and positive there, what we are getting is a minus. So we'll have minus EA over RT. Yes. So this is what we're going to have now. We've brought our activation energy divided by RT down, and we have it in this format. Now from there, we'll say at two temperatures, like that, T1 and T2, like that, we'll say we'll have K1 and K2. So we'll now say we'll have natural log of K1. Now what we are doing here is we are using this expression we have found here as a standard one, and then we are saying at two temperatures we're going to have K1 and we're going to have T1, and then on the other side we're going to have K2 and T2. So that's what we are applying on the other side. So doing that, we are saying natural log of K 1 is equal to natural log of A, that is subtracted by the activation energy, that is divided by RT, but the T at K1 is going also to be T1. So let's call this one equation number 1. Then equation number 2 will be natural log of K2 is equal to the natural log of A subtracted by the activation energy over R, then our T is T2. So at K2, our T is also T2. So let's call this one equation number 2, like that. When you reach this stage now, allow me to get rid of this down part here. Yes, let me get rid of that whole part there. So yeah, when you reach here now, what we are going to have is, we'll say, we're going to take equation 1 from equation number 2. So we'll take equation 1 from equation number 2. We can say that take equation 1 from equation 2, meaning we're subtracting equation number 1 from equation number 2. When we do that, we'll say what is on the left-hand side, we'll subtract what is on the left-hand side, and also what is on the right-hand side, we'll do the same. So what we'll have is, we'll have natural log of K2 minus natural log of K1, and this will be equal to, on the other side, we have natural log of A, that is being subtracted by the activation energy over R T2. Remember, it's the 2 that is being subtracted by 1. So this whole thing here will be subtracted by, we still have natural log of A, like that. That is being subtracted by the activation energy over R T1. Now this is temperature number 1. So that's what we are going to have there. All right. So let's go ahead and continue with our mathematics. Now I'm going to get rid of the upper part there so that we can continue from there. All right. So let me just rewrite what we have down here on top there. So continuing here, what we're going to have is still, we'll have natural log of K2 minus natural log of K1, that is being equal to, we'll have our natural log of A subtracted by activation energy over RT2, like that. That is being subtracted by natural log of A, and this will be added. Remember, when we multiply this negative by that negative, we're going to get a positive. So that will be added to activation energy over RT1 on the other side there. All right. So what we have here is natural log of K2 minus natural log of K1. Now on the other side, this and that will cancel. Since the signs are different, you can see this is positive and this is negative, and these are like terms. So these two are going to cancel. Yes, what will remain is minus activation energy over RT2 added to activation energy over RT1. Since the temperatures are different, we have T2 and T1. These two can't cancel. So let's proceed. This now will be equal to minus activation energy over RT2, like that. That is being added to activation energy over RT1. All right. So what we have here is the same as, we can start by writing the activation energy over RT1, then minus the activation energy over RT2. It's still the same. We can start by writing this or start by writing that. We are still going to have the same expression. What we mean here is writing x plus y and y plus x. These are basically the same. They'll still give you the same value that you get. For example, if we have minus 4 plus 2, this will give you a minus 2. And if we have 2 minus 4, this will still give you a minus 2. So whichever way you write it, you're still going to have the same concept. So this is what we are going to do here. We'll start writing the positive and then the negative instead of negative, then positive. So let's quickly do that. What we'll have there is we'll have natural log of K2 here being subtracted by natural log of K1 in that case, and this will be equal to now the activation energy over RT1 minus the activation energy over RT2, like that. So that's what we're going to have. When you reach this stage now, what we are going to do is on the left hand side here, if you have natural log, let's say you have natural log of x minus natural log of y. This is the same as natural log of x over y, like that. So this that we have here is the same as what we have there. So this is the same concept we are going to apply here. What is on the left hand side, natural log of K2 minus natural log of K1 is the same as natural log of K2 divided by K1. So that's what we're going to have there. And this is equal to, on the right hand side, we can see we have something that is common here. Activation energy and error are the same here and also the same there. So we can factor that out. And when we do that, we'll say we have activation energy over error. And then when we take activation energy over error on the first part, we'll have 1 over T1 remaining. And this will subtract by, on the other side, we'll just have 1 over T2, like that. So this is the formula we're driving. This is the formula we're looking for. Natural log of K2 over K1 is equal to activation energy over R multiplied by what we have inside there. So just make sure you can put this like this so that when you're doing your mathematics, don't get confused. We're not saying it's natural log of K2 then divided by K1. No, we are saying it's K2 divided by K1, then you take its natural log. So this is what we have here. Yeah, so that's our derivation for the Arrhenius equation. You can also derive it in another way. We can have K1 over K2, meaning in this case, we're taking K1 from K2. You can also take K2 from K1, and your Arrhenius equation will look different from this at 2 temperatures. But still, you are going to be getting the same answers, and this also is correct at this one. So you can have one that has got K1 over K2, and in here you have 1 over T2 minus 1 over T1. But if you found this video to be helpful, please subscribe to our channel, share, comment, and like so that we can make more videos like this.